Welcome to Video Wissen and a trip into the X-ray universe. My name is Traulsen from Leibniz Institute for Astrophysics in Potsdam, Germany. And if you'd prefer to see this talk in German, wenn Sie den Vortrag gerne auf Deutsch hören möchten, dann wechseln Sie doch zum Partnerkanal Urknall Weltall und das Leben. Dort finden Sie den auch. Today we'll travel into the X-ray universe. And usually you're invited to join our travels in a spacecraft, which brings you quickly to the science results. But today, let's take the plane to have a few stops in between and to see some of the aspects, what is on our way to retrieving our results. Why should you travel to the X-ray universe at all? Is there anything interesting out there? If you would have asked people a few decades ago, probably they would have said, no, not worth spending any time and money on it. But luckily, a few people tried anyway, and here I give you an example from my catalogue, what could be seen in X-rays in space. This is an image taken by the European X-ray satellite XMM-Newton, and the colors represent different energies, wavelengths. All the spots in there are X-ray emitters in the universe, often galaxies. This observation was taken in 2007, and then XMM-Newton looked at the same sky region again, quite some years later. Few of the faint points have disappeared, don't worry about that, that's just a matter of exposure time, but you can see that something changed dramatically. To the lower right, we have a very bright object in there. And then there was a third observation. About 2 years later, the bright thing has disappeared, but another one popped up. So there's quite something going on in X-rays, which might be interesting to study. I mentioned already, we are talking about telescopes in space, because X-rays do not penetrate our atmosphere. That's nice for us, but of course not perfect for observation. So we put our X-ray telescopes in space. Depicted, you see two of the major and old X-ray missions launched more than 25 years ago in 1999. The US-American Chandra and the European XMM-Newton. What do we see at X-rays, except for bright and fainter spots? We observe at high energies. So we go into the extreme processes in the universe, where it's extremely hot, where we have extremely strong magnetic fields, or where matter is transferred from one object, from a star or within a galaxy, to another object, another star, a black hole. We have the high energetic processes, which we see in X-rays. These processes are invisible to us in the optical, therefore it's worth going into the X-rays. And not knowing what's going on at these energies before, all those X-ray observations gives also a treasure of potential new discoveries. So in X-rays we have found object classes that were not known before, some of them considered in theory, and some are complete surprises. And we can also use X-rays to learn something about the evolution and the structure of the universe, so use it in cosmology. Europe's largest X-ray telescope in space is called XMM-Newton. It is a joint effort by many European countries and operated by the European Space Agency, shortly ESA. It was launched in December 1999, so meanwhile it is ESA's longest operated mission in space. It carries 3 X-ray telescopes, and an image of one of them is shown to the upper left. You can see that it looks quite differently from what you might be used to from guided tours at observatories, for example, because in X-rays we need a different technology to collect the photons, the radiation from space, which otherwise would just penetrate our detectors. So we use a grazing incidence where the radiation gets along the mirror shells into the focus of the detector and can be measured there. And to have a large collecting area, several of these mirror shells are nested into another. So we have, for XMM-Newton, for example, more than 50 mirrors. So this is the structure that you see to the upper left. On board XMM-Newton, there is another telescope where we can choose filters for optical and UV observations. just in parallel to the X-ray observations. XMM-Newton works on request, so scientists write their proposals, their applications to get time with XMM-Newton, and there's an oversubscription factor by about 7. So although XMM-Newton observes almost the whole year, scientists would like to see by a factor of 7 more data than they actually can retrieve, and obviously not all interesting projects that scientists would like to have can be run. Each observation becomes public after a predefined time span, and from then on, everybody can work with that data. To run such a space mission, we need a large team of people, and for XMM-Newton it is split in kind of 3 departments. There's the Missions Operations Center in Germany, which runs the satellite. There's the Science Operations Center in Spain, which works on the data, provides those to the observers and to the general science community. And then there's the so-called XMM-Newton Survey Science Center, which I'm part of. This is a group of people across Europe, originally at 10 different institutes, which provide software for data analysis and create and provide catalogues from all the observed data that XMM-Newton has taken so far. Here we are, the XMM-Newton Survey Science Center, seen on the map of Europe with an arrow pointing to the US, where there are another few people contributing to the software. And we mention on the map who is responsible of what. To the northeast, the needle there that sticks in me. I'm the person responsible of the source detection software and of one of the XMM-Newton catalogues. So as I mentioned, the SSC, this consortium of software developers and scientists, is responsible of providing software and catalogues to the public, to the science community. Here at AIP, we provide the source detection software, which means that in all images that were taken by XMM-Newton, we look automatically for whatever emits X-rays in these images. And our software is the basis of the catalogues which list all the sources observed by XMM-Newton so far. All that output is then used for research by the scientists, either to work on the data they have proposed, their very own data, or to work on the archive, or to work with those catalogues and study full object classes to look for a counterpart of their favorite object, to use whatever becomes public. Here's an example image from what a mosaic of several observations can look like, because as an introduction to the question, how do we get from the data stream, from a satellite, from a telescope, to something that scientists can work with? X-ray observations are a bit different from optical observations, not only from a technological point of view, but also from the way we retrieve the data, because compared to an optical image taken by your telescope, our objects are comparatively faint in X-rays. So we count each photon that reaches us from space. With a disadvantage, well, it's faint, it's not that much information, but with the big advantage that we can retrieve all information in one step with our CCD detectors, for which in the optical you would have to build 3 different instruments. So if we measure the arrival of a photon in our detector, we know about its position, and putting all these together, we get an image, brightness over position on the detector. We know the arrival time of the photon, so we can construct a light curve knowing how many photons arrived within which time span. This is the yellow curve in the illustration as an example, brightness over time. And we see its color. We can measure the energy of this photon and create a so-called spectrum, which gives the brightness over unit energy. And this spectrum can be a bit compared to a rainbow. In X-rays, it codes the different colors, which you also could call energy or wavelengths, that we measure, and transports quite some information about the physical processes that are going on. Let's switch to the optical quickly just to illustrate how this works. We start from a well-known constellation in sky, the Orion, and zoom a bit in. These images are taken from the ESA Sky Tour provided by ESA. And we now focus on a target that is, on the first glance, a bit boring in the optical because it's not very bright. And now we switch to the X-rays and take an X-ray image. In the upper part, you see the image. In the lower part, in yellow, we create a light curve, so that brightness over time. And now let's start collecting photons with XMM-Newton. The light curve in the lower part is whatever is found within this white circle. And you can see photons tickling in. And this is a time-lapse video, so this is much faster than the actual observation. You can see something changes, but in total, really you see individual photons arriving. And now we start to accumulate these. This was just how they come in. Now we accumulate these and create an image from our measurement. Again, in the lower panel, you see the light curve and the moment where this central object becomes really bright. By the way, this is an interacting binary star, and we see its orbital cycle, therefore the brightness changes. Now that we can count photons, we can do something with them. And the SSC consortium and a team of the European Space Agency provide a full suite of software packages to work with these data. This is meanwhile more than 300 individual tools and, let me check, I think 12 or 14 or so developed and maintained by me. All these software packages cover the aspects from retrieving the data, converting them into something that people can work with, to calibrate them, to have a reference scale for precision, for energy, for arrival time, to learn something about the area of the detector that we can use. Was there any bad pixel in between, for example? How was the background level during the observation? That is both instrumental background, but also solar activity triggering the measured background. And then we can create those products that I mentioned, and from where the science starts, the images, the light curves, the spectra, and additional data. And the software suite also includes the tools to do the science analysis of these data from your XMM-Newton observation. Which ones are now my favorites and my tools? I am responsible for the source detection, which means searching automatically for X-ray emitters that we had in our image. Here you see a full field of view of XMM-Newton, which corresponds approximately to the size of the moon at the sky. So normally our observation or our proposer will be interested in the central target, given a good justification why it's interesting to observe this. But within the large field of view, we will find between a few tens and several hundreds of additional X-ray emitters in the sky, which might be interesting for science as well. This is what our software is about. And to improve this search finding, to have good results, we need a few information which are listed here, which is the usable CCD area. Where do we collect valid photons at all? It's called a mask. We model the background that I mentioned before, the instrumental plus the background triggered by solar and space activity. And we need to know which pixel in the CCD was exposed for how long. Knowing all this, we can start to model our source. To the left, you see an image as measured by XMM-Newton. Now the color just codes the brightness, no information about wavelength or energy shown here. And to the right, this is the model image that we can produce for this source, taking into account everything we know about the instruments. And you may be a bit surprised to see a star structure, an asterisk in there, although you probably have learned in kindergarten that is not the way a star looks like, and when we start drawing them like that. This is the spider structure from the instrument. You may remember the photo shown before with the mirror shells. The spider structure, which keeps the mirror shells in place, that gives this reflection or this spider structure in the image as well, and this is modeled. And now we would like to have a good agreement between the model image and the observed image. So we shift that, we change the brightness until we have best agreement between our model and our measurement. And through statistical evaluation, what is best agreement? And if we have reached that, then we know something about the position, about the brightness of our object. Looking at these images, you may consider it a bit boring because we could just point to that. It's obvious. There is a source in that image. It becomes a bit more difficult if the sources are fainter. Then it becomes difficult to distinguish our celestial source from the background in the instrument. And there we really need the statistical evaluation. Again, to the left you have the measured image, to the right you have the modeled image. And there we provide kind of a likelihood of a probability that something our software finds is indeed a celestial object and not just a fluctuation in the background. Now switching from a small part of the detector to the full detector, you can see what I mentioned before. There are many hidden sources in this image which was taken to study the bright central source, again one of these binary stars. Having run the software, we can provide the users with a full list of information on all sources that we have found in this field, which is an identifier, so we know what we are talking about, the coordinates in the sky to find it again, to run a follow-up observation. The extent, is it just a point source, or for example with a galaxy, something largely extended, how bright it is, under which conditions was it seen, was there high or low celestial background, and many more information that scientists can use for their studies that are derived from these main items that I showed before. Now, going one step further, my job is not only to perform source detection, but I'm also specialized in combining observations. You may also know this from the optical. The longer you expose your image, the more you see in it. And it does not have to be necessarily an observation in one row. We can also combine observations that were taken about a time span of several years. That's what I'm showing you here. Then focusing on a white dwarf, and this one was observed quite frequently by XMM-Newton. Now let's add these pictures. We go from one observation to the next, and you can see that more often we observe, if we combine those, the more objects we see in there. And these overlapping observations are one of my main focus for the source detection. And it is worth doing that because meanwhile, after more than 25 years, about 2/3 of all XMM-Newton observations taken have some overlap pattern with another observation, where we can deeper than with the analysis of an individual observation. So we can discover the fainter X-ray sources by combining all the observations we have, and we can also look for variability, what we had at the beginning of this talk, something getting brighter and fainter every now and then. You're showing another example, just 9 observations this time, and I put some arrows in there to indicate where it might be interesting to look at if I scroll through those 9 observations, because every now and then you will see something pop up and disappear at one of those arrows. So we can use the stacked source detection, the combination of all the observations we have, to search for objects that change their brightness with time. And there's a variety out there in the universe. This can be stars, this can be binary systems, this can be active galaxies on timescales from hours, days, up to years. And within an observation, there are also objects studied on a timescale of less than a second, which vary very rapidly. Now that we have created our source lists, we would like to combine them and to provide all the information to the users. This is partly done here. So the source detection, the search for X-ray emitters in the images, is done on individual observations by ESA. And on those overlapping observations, the stacking, that is done by me. And each of these source detection runs is also followed by a quality control. How likely is it that what our software has detected is really a celestial object. This is partly done by software again, and it's partly done by eye and experience. And this is an example from this so-called visual screening that I do with each catalog release on a yearly basis. And everything marked in there in red is indicated as problematic. So the software found something there, but I can see that something happened that I would not like to be considered a celestial source in our catalog. So you can join me in this exercise, not only to become a trained XMM-Newton screener, but also to get an idea of what is in those catalogs. So my job is not to do a classification of all those discoveries, but of course I'm also interested in knowing what it is. So I picked a few examples and you can help me screening. I know I have not trained you so far, but just guess, what do we see in the center of the images that I will show you? Is it just a problem with the detector, something that is not worth including in the catalog? Is it some kind of background emission, or is it really a celestial object that our proposers, our users would like to study? Starting from this one, bright spot in the center, yes, this is a celestial object. This is an active galactic nucleus, a galaxy which has a supermassive black hole in its center. And this black hole accretes matter from its environment. And the infalling gas, which can be stars, planet, whatever, the infalling matter is heated and, as I said before, energetic processes. That's something to be seen in X-rays. Next example, reddish stuff. Is this really celestial? Yes, it is. We are back by my favorite topics of interacting binary stars. This is a very close binary of an old star, a so-called white dwarf, and a companion star from which matter flows onto the white dwarf. And this matter gets heated when it arrives at the white dwarf surface. Again, we have a high energetic process that we can study in X-rays. I know that it is a compact binary because this is one of the objects that I studied for my thesis, but just looking at the images, this reddish stuff, which means X-ray soft, as we call it, this could also be another fascinating object, a so-called isolated neutron star. So this is a star, a sun-like star, compressed to a size that would fit into the area of Berlin. So this is a really exotic matter and fascinating to study, also because these objects are essentially only seen in X-rays. They are so faint in the optical that even the biggest telescopes have problems catching those. So these are found in X-ray observations. Next example, again, reddish stuff, but now elongated. This comes from space, but it is an ionizing particle. It's nothing that we would like to study for astrophysics, like a star or a galaxy. Next question. Again, reddish stuff in there, elongated. What is this? This time, it's not a detector issue. This is a celestial object. This is Jupiter. And indeed, our planets in the solar system reprocess the X-ray radiation by the sun. So we see our planets in X-rays. And because this is a combination of several observations and Jupiter seems to move on the sky, we have this path of Jupiter on the sky that we see here in this combined image. Strange shape, detector problem or celestial? It is celestial. This is a galaxy seen in X-rays. We see the hot gas in the galaxy, and to the left you have the comparison image in the optical. It's quite different, so it's obvious we study different physical processes in different wavelengths here. Again, back to reddish stuff. What do we see here? Yes, this time it is just a detector. This is just stray light because we have different instruments within XMM-Newton, and from the beam splitter, from the technical details that bring the light onto the detectors, there's this stray light pattern. And unfortunately, typically this kind of stuff is only found after the launch when you have no chance to work on that anymore. We have to live with it and exclude it from our analysis. Stripes again. What do we see here? Something from space or not? Again, this is a celestial pattern. Again, we see the mirror shells and this spider-like structure that holds them in place. And these mirror shells give this reflection pattern if we have a very bright optical source next to our observation. This is unavoidable. It can be still interesting to run these observations. You see some brighter points in there. These sources can be studied, although we have some problem with the detector stray light here. Once again, concentric rings, something interesting or something to remove. It's a thing which is difficult for source detection, but extremely interesting for science. This is an afterglow of a gamma ray burst. We still don't know exactly what a gamma ray burst is, but we can observe bright events in the gamma energy range. And after some time, the radiation from this burst starts to be seen in X-rays in the surrounding gas. And these rings that you see here by the excited gas around the event can be used, for example, for extremely precise distance measurements. Once again, strange structure on our detectors. Yes, this is from space. It is quite a nuisance for source detection because we are looking for certain predefined shape and not for these large extended targets. So for source detection, this is a problem, but for science, this is very interesting. This is a supernova remnant of a star explosion to the left. Again, the comparison to the optical. There's little to see, but in the X-rays, we see all the hot gas surrounding the position of the star explosion, which took place, if I remember correctly, in 1100 something or so, long ago. But we still see the glowing gas in X-rays. Another strange structure on our detector, what would you guess? Again, as before, nuisance for source detection, great for science. Another supernova remnant, that's how this hot gas can look like as well. One more example, what do we see here? Again, it's celestial, and it's something which is really taken well by our source detection software and very interesting to study. We are now going to even larger structures in space. Each of these brighter areas is a cluster of galaxies, so several galaxies like our Milky Way and the surrounding galaxies that are bound by gravitation, and in X-rays we see the hot gas surrounding and between these galaxies. So having collected all these, we can now construct a full catalogue from our source lists, which is again partly done by a partner institute, that's the IRAP in Toulouse, and partly done here by me. And just as a quick teaser, we are currently joining efforts. So far, we have published catalogues from individual observations and catalogues from overlapping observations separately. The next catalogue will be done here. I'm currently retrieving the data, and the next catalogue will be produced at AIP, plus input from many other institutes, and will be a combined full catalogue of everything. We also publish some so-called auxiliary products for each of those groups of observations that we process and for each source that we find, not only for entertainment, but also to help the scientists to study the observation conditions and the objects that they see. And if you would like to have a look at the catalogue, I do not expect you to read all the details here. I just wanted to show you one of the websites where these catalogue databases are provided. This is the edition by the ESA. You will find the QR code if you would like to look into it and to really read it. It's a small excerpt from my catalogue listing the sources and their main parameters. I have cut from this screenshot a few hundred more columns that give information about the source observed. And maybe you see those colored things in there. These are thumbnail images. These are part of the auxiliary products. So for each source that I find with my software, I provide two kinds of X-ray images. These are the upper panels. I provide a long-term light curve. This is brightness over days and years, whatever is collected by the XMM-Newton observations. And also to the lower right, an optical finding chart, which you could use for a follow-up observation to point your private telescope to this target if you're interested in it. So what has happened over, meanwhile, 25 years of XMM-Newton observations is shown here. All those bars inform you about the contents of our catalogs. The first one published in 2003, the latest one just under construction, and the bluish bars show the number of sources and measurements in there. The green bars show the number of observations that we used, and the most recent catalog, this is the one that will be constructed from the mentioned 17,000 observations. And I give you a quick estimate. It's not that the analysis, but an estimate how many measurements we will list in this catalog. Please don't copy it. You will get the right numbers in a few months. Again, if you would like to see more about that, there's a QR code and a link in this image. This is our local web page at the AIP with all the information about these catalogs and also download options and links to those online resources that I showed before. Why do we do all this work? And why should we provide the science community with our software and catalogs? They are used for systematic searches, for new candidates in known object classes, like those isolated neutron stars, for the completely unknown and the surprises. Giving a few examples here of the object classes that are studied with XMM-Newton and that are studied within our catalogs, like star-forming regions, active stars. You have seen the image of a planet before in our own solar system. Those close binary stars, accretion processes are not only there, but all over the universe. Outbursts, stellar explosions, black holes in binary systems, or the really massive ones in full galaxies, large-scale structures, galaxy clusters, and beyond cosmology. For all these topics, our catalogs might be helpful. You can study short and long-term variability in them, and those people who do not mainly work on X-rays, they still can have a look at those catalogs if they would like to know whether there's X-ray emission from their favorite pet object discovered at, say, radio, optical, infrared wavelengths before. And if you would like to learn more about that, in the YouTube channels Video Wissen and Urknallwelt an und das Leben, you'll find quite some examples of scientists reporting on their discoveries and work done in X-rays. And in quite some of these talks, you will see the name XMM-Newton and maybe have my catalog mentioned. Thank you for your attention.